Okay, what we were up to was coming up with this controller here. Get this feedback system to do what we want. And we're using Root Locus to do it. We've already gone through one example. A reminder, we're only considering 3 types of controllers, and I'm only going to talk about 2 methods. Here's a lot more other controllers. We're only going to actually go through about 3 of them. And here's an example I'm going to continue. We already did it one way using one method. We're trying to come up with this controller, G sub C here. This plant is a given. In this case, it's unity feedback, and we have certain specs. Here are the 2 poles of this part of the system. And to meet these specs, we need it to be left of this dashed line and below or left of these slanted lines. So somewhere, well, anywhere over here is okay, but we don't want to be too far from the boundary. And I'll get into it, but we picked a design point of, I think it was -5 plus or minus J 6.8 to meet these specs. If you, let's see, we went through this. If you just look at the root locus, if we just use proportional control, here's the root locus in that case on this solid black line, and we never get to the left of this dashed line, so we can never meet the settling time spec with just proportional control. We went through a move the bad pole method, and I'm not going to go through that again. So I'll just skip all that. But anyway, yeah, here's where we said we want the design point. And that's what I said. And actually, if I had to do this over again, I wouldn't put it so high up. I'd make this more like 6 instead of 6.8 to be more comfortably inside that boundary. Now we'll get to the second method called the bended method. The first method we called move the bad pole. So now we'll call it the bended method. We're still doing the same. It's the same system as before. Here's the plant. Here's the design point, which I'll just say is a given. We'll look at 2 different controller types. One is this ideal differential, I believe, where we just add a 0 and a gain. So overall L for our root locus is this. There's a new 0 here, and then we'll have to figure out what the gain is. The second controller, I think I'll wait till another video for that. But if we do this one, we have the 2 poles from the plant, and then we're adding a 0 somewhere. Right now, we don't know where it is. And up here is the design point. Can we put this 0 someplace where the root locus goes to that design point? Okay, let's figure out how to do that. Well, before we went through from the complex arithmetic of the characteristic equation, you had that the angles from all the poles and zeros had to have a certain relationship. If you add them all up, I think it was the zeros minus poles, it had to be 180 degrees. So if we do that, you get a formula for the angle from this 0 to that design point. And you get it by this arithmetic here. Angle is the sum of the angles from all the poles minus the sum of the angles from all the other zeros plus 180 degrees. And you calculated those angles by this equation. You're using the design point and whatever polar 0 you're talking about. We have we're looking for the angle from this zero to that design point. And in this case, well, here's that formula repeated again. All the poles minus the other zeros. In this case, there are no other zeros, so we just want the sum of the two poles. And what is it? The design point, the imaginary part is 6.8. Imaginary part of this zero, or actually no, to this pole, well, to any of these poles or zeros is going to be the imaginary part is 0. They're all in the real line. We're actually doing the angles, this angle and that angle. And that's this angle of the 0 is the angle from that 0 to the design. So the difference in imaginary parts is 6.8. Real part of the design point, that's at -5. This pole's -3, so minus of -3 is +3. This pole, everything was the same except it's -1. Do all that arithmetic, being careful with your calculator with those inverse tangents. And you get a number, 46.9 degrees about. That's the angle from here to there. Once you have that, let me see if I can go up. So now we know this angle up to that design point. It's a little over 45 degrees. If you look at the trig of that, think of this triangle. We know this side here. That was the 6.8. And now we know this angle. So we can find this leg of that triangle, and we know where the design point is on the real line, so we can figure out where that 0 is. Did that little trig, it says here's where the 0 is. It's a little formula. Put it on your formula sheet. And then we'll also have to calculate the K. So let's calculate this Z. The imaginary part of the design point is 6.8. The angle was 46.9, so it's the tangent of 46.9 minus the real part of the design point, which was -5. Put this in your calculator, you get 11.4. So this 0 is at -11.4. And what's the K? The overall L, where is that? Well, L is going to be, I got it somewhere. Oops, what happened there? The L is going to be the product of these two guys without the K. So we have a 0 up here, which is at 11.4. Z is 11.4, which means the pole is at -11. L is the product of these two guys. To calculate K, you flip that upside down. So you have S+1 and S+3 on the top. And you plug in for S, the design point. Right? That's how you calculate K. You have a previous video on that. So here's the design point, -5 plus J6.8 plus the 1, and then -5 plus J6.8 plus the 3, all over that design point, plus this 11.4. Remember how to get these magnitudes? Well, this will be -5 plus 1, so it's -4 squared, or 4 squared plus 6.8 squared. Use Pythagorean theorem. That's how you get these magnitudes of complex numbers. Do all that arithmetic, you get a 6. And there's our controller. Here's the whole, that forward loop. Forward loop gain, forward loop hit. What do we have? So here's what the new root locus looks like. The root locus is going to like come up here. One will go towards the zero, the other will go to minus infinity. One went down here, and went one of the two ways. These were the magnitudes. This is the K. It's the L flipped upside down with your design point plugged in for this S sub zero. It's these two magnitudes divided by this magnitude. Anyway, we have our controller. We go through, then we put it in MATLAB and see how close it comes to meeting our design specs. Here's what the MATLAB Root Locus now looks like. Like I said, these two poles come together. One goes up here, the other goes down here. One goes right, just the zero. One goes left and minus infinity. We don't quite meet the specs. Well, we meet the selling time spec, but not the peak overshoot spec, because we have this zero, which is, remember, that kind of changes meeting the spec. It makes the overshoot bigger. I would probably change the design point, but what I made my students do was just hit the design. We'll worry about iteration later or changing the design point ahead of time. I'll worry about that. My students worried about just doing all this arithmetic that we went through. I'll do another example of the bend-it method with this controller instead of just having a zero. I'll save that for another video.